Hello friend, let us move on the unit number 3, 2D elements. In this one, we need to do a study of introduction to the 2D element. Now what we learn from this unit? In this unit, we need to do the study of the two-dimensional stress analysis, where we need to focus on a plane stress and the plane strain problems in 2D. Then we need to understand what is mean by the plane strain and the plane strain stress in elasticity, as well as we need to derive the constitutive relationship. In this one, we need to consider the element constant strain triangle and the linear strain triangle, and through that one we need to solve the finite element analysis problem. Here we need to define first of all the displacement function for the 2D, and when we are designing or the developing the shape function, that time how to develop that relationship of the displacement function is to be considered through the Pascal triangles. We also do the study of the compatibility, that is the continuity and the completeness requirement, as well as the geometric isotropy. We need to work on the convergence methodology, strain field, stress field. We we here there is a very important issue is that we need to focus on the formulation of the element stiffness matrix derivation and the load vector for the plane stress and strain problem derivation. We need to do that study also. Similarly, as we are already knowing that how to do the assemblage to get the global stiffness matrix and the load vector, applying the boundary condition and solving the primary problems, means for the displacement and the stress we need to do study into this chapter. Overall, this is somewhat difficult comparative to the first one, because in the first one we only consider the 1D elements, the bar having a very simple linear relationship. But when we go for the 2D, then we need to consider the CST or the LST element, and when we consider the CST and LSR elements, that time at every node there are the 2 or 3 different types of the degrees of the freedoms are available, and because of this 3 or 2 degrees of the freedom, the matrix developed is a very larger one, that may be a 4 by 4 matrix or the sometimes the 6 by 6 matrix, and ultimately it makes a lot difficulty to solve the problem. So let us move into the unit number 3, 2D elements. So what is that? 2D elements is are defined by the minimum 3 to more nodes in 2-dimensional, as I already mentioned. And in this one we need to do the study of a plane stress and the plane strain analysis. Now this is the plane stress and plane strain analysis is very important. If once we are understanding this one, then there is no issue at all. Then we knows very well majority of the problems in a 3 dimension, but we knows, even though if we go for the 2D analysis, then also we are getting the one accurate solutions for this one, and for this purpose we need to do the study of 2D elements. Here we need to understand first of all the concept of the interpolation and the numerical integration. Here we are not focusing on the concept of the interpolation and the numerical integration, that we studied later on. Here we are focusing on the equation of the elasticity. Now stress. What is stress? Stress still we are not understanding in a right way. We are considering the stress is the very simple formula, that is force upon cross sectional area. But actually the stress is a tensor quantity, and when we are defining the stress in terms of the 3 dimensions, then we need to write the stress is equal to in the format of the matrix sigma xx, that is along the x-axis, then the sigma y-axis, then this one is the sigma. Here there is no x, this should not be written here. So let us take now this is the simple object we need to consider. Let us take this is the simple object which couldn't have the thickness, so this is only the simple plate I need to consider. Here we applied the force along x-axis, the force applied on the x-axis, then the forces applied along the y-axis, and the forces applied along the y-axis, while there is no force along the z-axis. There is no force along the z-axis, because this is the plate. It has only the very small thickness, that's why That's why there is no z-axis force. So these are the normal forces. These are the normal forces. So this is the my x direction force. This is my x direction force. This is my y direction force. So this is my y direction force. Now because of this x force and the y force, there is a stresses develop into this plate. So when the stresses are developed along this one, so here we could say that there is the development of the sigma x, that is the normal stress along the x axis, then the normal stress along the y axis. So this is the y axis. Now because of this elongation, there is a possibility of distortion of this plate. So this distortion looks like this one. So this distortion is possibly looks like this one. The plate is distorted like this one. This is the distorted form of a plate. This is the distorted form of the plate. So when these forces are applied, that time there is a there is a shear stress is applied on this one. Now how to write this shear stress? Now this shear stress is a tau. Now this applied on this surface it applied on this surface. So this surface is a y surface. So this is the y surface. So I could write this is on what applied on the y surface and along the your x-axis. So this one is along the x-axis. Hence I am writing my shear stress, that is the tau along applied on a this edge is my y edge. So first of all I am writing this one is the y, and then along the x-axis, so this is the x, I need to write this one. So these are the stresses applied. Now this is the normal stress along the x-axis, means this is my stress along x-axis. Then this one is the my stress along y axis. So this is my along y axis, and lastly this is my z axis. So this is the z axis. So here there is no z axis, so there is a this term could not come in picture, but just from the theory of elasticity I am writing this theory matrix. That's why this one is the normal stresses. So these all perpendicular parameters are the normal stresses which applied on this plate, while other stresses are the shear stresses. This is the shear stress, this is the shear stress, this one is also shear stress, this is also shear stress, and this one is also a shear stress. So diagonal elements are all are the normal stresses, and this another stresses are the shear stresses. Hence just to define a stress in a right manner, we require the tensor. That tensor is a very important factor or the important mathematical parameter which we have not studied into the mathematics in a right way. We only learning the matrices, and through the matrices we are trying to solve this one. Now the second concept is maximum distortion theory. So in this theory what we are learning, that what type of the theory of a failure we are using whenever we are designing the different types of the component. So generally we are using a one masses theory. So in a one masses theory, we could say that whenever the stresses reaches beyond the one masses stresses, then there is a failure occurs, or yielding is possible. So this is the formula for maximum distortion theory, that is the sigma one masses theory. One masses stresses is equal to, this is the formula, that is the sigma x minus sigma y whole square, sigma y minus sigma z whole square, plus sigma z minus sigma x whole square, plus 6, that is the tau, that is the shear stress xy square, plus tau yz square, plus tau zx square. Again this formula is applicable for the 3 dimension. So this is the one masses theory of a failure. So what it suggests? It one is suggesting that the yielding is possible when the one masses stress must be equal to or greater than the yield strength of a material. Or I would say that the material is goes for the failure if this the developed stresses is lesser than this one masses stresses, and this one masses stresses is a scalar quantity, not a vector quantity. So keep in mind this is the scalar quantity. Next parameter, that is the defining the different differential equations for the differential equation from the theory of elasticity. So we need to define the equilibrium equations of a for by using a differential equation from the theory of elasticity. Here we consider this diagram, and accordingly we are trying to solve the formulation of a differential equation. Let us move on this one. Now again, here this one is the dx, this is the dy, this is the dy, the distance between this plate, this is the distance between this plate. Now here the force sigma y stress is applied, this one is the sigma, here that one is the sigma y is applied. Now because of this distortion taken place, this is the value come out here, and this is the sigma, so this one is the sigma x force is applied in this direction. And now because of this sigma, there is the stresses develop on this way. So through the equilibrium theory, what we have studied, that is the since this one is the variable, there are the two variables x and y. So these two variables we need to differentiate, we need to differentiate. Now when we are going for the differentiating this one, then it could not be possible, since because my function is depend on the two variables. Since the function is depends on the two variables, that's why I could not be differentiate. Instead of that, I need to go for the partial derivative of this one. So dabba by dabba x, dabba by dabba x. So here you can see that dabba sigma x divided by dabba x plus dabba tau xy upon dabba y, then dabba tau z upon z plus force, that is fx along the x-axis. Similarly, this here also dabba tau x y upon dabba x plus dabba sigma y upon dabba y plus dabba sigma yz upon z plus fy is equal to 0. So these are the equations we have developed. These are the equation developed for the 3D. But we knows very well, in 2D problems, Z parameter is 0, your normal stresses along the Z is 0, as well as your shear stresses also along the Z axis is 0. That's why this total Z term is cancelled, this total Z term is cancelled. Okay, so whatever the things are remain, that we are writing here. So what we are writing here, that is the dabba sigma x upon dabba x plus dabba tau yx upon dabba y plus f0 is equal to 0, and this one is the second equation. So these two equations we are considering the equilibrium of the plane element, which we are using for the next studies. Now there is the necessity to develop first of all the stress strain relationship. Now strain and displacement relationship. So strain you know very well. So whenever we are applying the forces, that time the strain is occurs like this way. So the first of all, the strain epsilon x along x-axis, that is dabba u by dabba x, dabba u by dabba x. So dabba u by dabba x. So this is the dabba u by dabba y. So along x-axis you need to write the dabba u. So and the epsilon y strain along y-axis, that is equal to dabba y v by dabba y, and your tau xy is equal to dabba u by dabba y plus dabba v by dabba x. So these are the equations useful to define the strain displacement relationship. What is this? This is the strain along y-axis, normal strain along y-axis, normal strain along y-axis, and this one is displacement with respect to x, displacement with respect to y, and this one is the your tau xy, sorry, gamma xy, that is the shear strain along x, applied on a x surface along y-axis, then that is equal to dabba u by dabba y and plus dabba v by dabba x. If you look here, there is the change here in a sigma x, this is the dabba u by dabba x, while here this one is the dabba u by dabba y, not the x, so keep in mind, you don't be confused this one, because later on we need to use these formulas many times and you do not commit this mistake. Then we are going for the stress strain relationship. So instead of going in lot details, I need to force you that you need to keep in mind these formulas. These formulas playing the very important role whenever we are solving the certain equations. So these relations are related with the E and the Poisson's ratio V. E and Poisson's ratio V. So keep in mind these are the different formulas. And the last formula, that is relationship between the elasticity, modulus of rigidity and the stiffness. So this is the relationship. So this relationship not much use into the FEA, even though this relationship also not use a lot, this relationship also not using a lot. That's why I'm not focusing a lot on the stress strain relationship. Instead of that, you need to focus on these parameters. These one are playing the very important role into the finite element analysis, as well as these parameters also playing the very important role into the analysis. So thank you to all of you for watching this video.